Now it's important that you actually find the Hessian and then find its determinant to see what's going on. Now, here's an example. If I find the gradient of this function, the gradient of this function would be, let's see, the partials with respect to x would be 0.9x plus 2.2y, and the partials with respect to y would be, let's see, 2.2x plus, oh, I did this wrong, this should be 1.8x, sorry, 2.2x plus, take the derivative of this, and we get 1.8y. Now, to find critical points, we have to figure out where is this gradient equal to 0. Okay, let's see. Now, it might help us to divide through by, well, we could multiply by 10 and divide by 4, multiply by 10 and divide by 2. Okay, so we multiply by 10 and divide by 2 with this equation. See, multiplying by 10 would give you 18, divided by 2 would be 9, so we have 9x plus, multiplying by 10 here would be 22, and then dividing by 2 would give us 11, and then this becomes 11x plus 9y equals 0. Okay, so we can see that if I were to take 11 times the top equation and negative 9 times the bottom equation, then I would have 99x and negative 99x, and so those would cancel. So taking 11 times the top, we have 99x plus 121y equals 0. Taking negative 9 times the bottom, I guess, oops, I took positive positive 11 times this. Take negative 9 times the bottom gives us negative 99x, and negative 9 times this would be negative 81y. And when I add those two equations, the x's cancel. 121 minus 81 would be 40, so we have 40y equals 0, and therefore y equals 0. Of course, if y equals 0, we could go up to either of these equations and find that 9x plus 11 times 0, which would be 0, has to turn out to be 0, so x has to be 0. So we have just one critical point, one place where the gradient is 0 in this case. So it's at 0, 0. So we have a critical point. At 0, 0. So what we want to do now is to calculate our Hessian, the second derivative matrix. See, the partial f sub xx goes up here, so that's going to be 1.8. F sub xy is going to go over here, 2.2. F sub yx is going to be 2.2 as well. Remember, we expect that to be the case because we have this function all of whose derivatives are continuous, so we know the mixed partials should all be equal here, and now f sub yy would give me 1.8. So you might look at this and say, well, look, f sub xx is positive. That means if you look in the x direction, the graph has to be concave up, and f sub yy is positive, it's 1.8, so if you look in the y direction alone, just freeze the other variables, f sub yy is positive, and so it's going to be concave up that way. Doesn't that mean it has to be concave up in all directions because it's concave up in two directions? And the answer is no. You can still have some direction that's sneaking down here. And if you actually take the determinant of the Hessian, then you get a negative number here because you take 1.8 times 1.8 and subtract. So we have 1.8 squared minus 2.2 squared. You can see this is going to be the bigger number, right? So the Hessian is going to be less than 0, and in the less than 0 case, we know that we have a saddle. So the point of this example is just to say it's not enough just to look at f sub xx and f sub yy. Just because it's concave up in two directions doesn't mean that it's concave up in all directions. But if the determinant of this Hessian is positive, then you know that it's either concave up in all directions or concave down in all directions, and you can look at the concavity in one direction and then be able to say, since the determinant was positive, that it has that same concavity. But if the determinant of this Hessian is negative, you know there's some direction where it's concave down, and so that you're actually at a saddle. It'd be fun just to plot this one. So let's look at Maple here, and we'll use Maple to graph this. So we've already loaded our plotting package, so we just need to use plot 3D. So we'll plot 3D, we have 0.9 times x squared plus 2.2 times x times y plus 0.9 times y squared. And we just need to make sure we contain the origin where we examine this. So we could just go from -1 to 1 and y from -1 to 1. Okay, and we get our graph. And if you look at this graph, sure enough, let me pull it up so you can see it good. Oh, maybe let me put some axes on here. Axes, just normal. Put some axes on here. Okay, now this is my, there's my x-axis and there's my y-axis. If you look at this, it's ever so slightly concave up in the x direction. Also, it's concave up in the y direction, and yet if you look at it in one, there is a direction in which it's concave down. So this is why we actually have to compute the determinant of the Hessian. It's not enough just to look at f sub xx and f sub yy. It's possible for a function to be concave up in two directions, concave up along the x-axis and concave up along the y-axis, and yet still be concave down in some direction. And so if we look at the determinant of the Hessian, we can tell, because if the determinant of the Hessian, that 2 by 2 Hessian, is positive, then you know that it has the same concavity in all directions. But if the determinant of the Hessian is negative, you know that it has positive concavity in some directions and negative concavity in others, so you have a saddle.